The central limit theorem arises from independence. In the basic central limit theorem, we assumed independence and identical distribution for all of the random variables, but that second assumption is not strictly necessary. However, we can't abandon it altogether. We need some kind of average uniformity for our random variables, at least in the tail, in order for the central limit theorem to hold. Here's an example to understand why. Suppose that xn is a sequence of centered normal random variables with some variances bn squared. As usual, let Sn be the sum of the first n of these random variables. Now we know that we can construct the distribution of such an xn in the form bn times z, where z is a standard normal random variable. And that means that we can quickly calculate the characteristic function of xn. It's the same as the characteristic function of bnz, which is the same as the characteristic function of z with the variable xi scaled by bn. But we know the characteristic function of a standard normal, so this just gives us e to the minus bn xi squared over 2. Now, given the independence, we can therefore compute that the characteristic function of the renormalized sum Sn over root n at xi is the same thing as phi of the sum of the x's at xi over root n. But the x's are independent, and so that is the product phi x1 at xi over root n times up to phi xn at xi over root n. So that gives us this product of exponentials, where the only difference from term to term is which bk squared appears in the exponent. In other words, this is equal to e to the average of the bn squareds times xi squared over 2. Now, if all of those variances bn squared are the same for different n, or even if they just converge to some fixed variance b, then of course we get that this converges to e to the minus b squared xi squared over 2, which is the characteristic function of a normal distribution with variance b squared, and that covers the usual central limit theorem that we have proved in this special case where the terms are also Gaussian. But we could consider other sequences of bn's. For example, what if bn were equal to the square root of n? Well, then that sum of the bn squareds is this quadratic function of n. And that means that the characteristic function of the nth term in the sum renormalized is this, where the n's cancel, but we still have linear growth in n. And now, what happens as n goes to infinity? Well, this is the characteristic function of some law, the convolution of all of these Gaussians, and every characteristic function is 1 at xi equals 0, which we can easily see from here as well. But if xi is not equal to 0, then as n grows, this decays exponentially fast to 0. And so here we see a concrete example of a sequence of characteristic functions that converge to some function which is not continuous at 0, and therefore is outside the realm of the continuity theorem. This sequence of random variables, xn, does not converge weakly to anything. And in particular, the central limit theorem, of course, fails. What's going on here? The laws of these rescaled random variables, which are Gaussians with these variances here, are spreading out more and more as the terms go on in the sequence. And so although the mass is always concentrated near 0, the degree of concentration is getting less and less, and asymptotically, the mass actually all escapes to infinity. You can work out that, in fact, the sequence of laws here actually converges vaguely to the 0 measure. So we do have to be careful if we want to generalize the central limit theorem. We need some condition that's weaker than identical distribution, but still encodes the notion of all the random variables being around the same size. We can capture that using our intuition from our development of infinitely divisible laws in terms of triangular arrays. Our standing assumptions now and setup are going to be that instead of having just a single sequence of random variables, we'll have a triangular array of random variables, x and k, where for each n, k ranges from 1 up to n. We'll assume that these are all independent along each row. We don't care what the relation is between the x and k's for different n's. They'll all be L2 centered random variables. And just for notation, let's let sigma nk squared denote the variance of the term xnk. Since they're L2, that is finite. And given such a triangular array, we denote by Sn the sum of the terms in the nth row. Now we can put our basic central limit theorem setup into this framework. For the basic central limit theorem, we have a single sequence xn of IID random variables, all of some fixed variance b squared, and then we look at the sum of the centered random variables divided by the square root of n times b. Why is that the right thing to rescale by? Well, we can quickly calculate from the independence that the variance of the sum, centered or not, is the sum of the variances. In that example, all the variances are b squared, and so this is n b squared. Which means that the thing that we're normalizing by here is the square root of the variance of the sum. That's really what it means to standardize. You take a random variable, you center it, and you divide it by its standard deviation. The central limit theorem says if you take a sequence of IID random variables and standardize the sum, that standardized sum converges in distribution to a standard normal. Using the triangular array approach, we'd just be setting xnk to be the centered version of xk divided by b times square root of n. And in so doing, we've arranged it so that the variances of these sum up to 1. That's going to be our standing normalization, that the variances in a triangular array will add up to 1 along each row. That means that we are standardizing the sums in each row to start with, and so a central limit theorem for a triangular array will be a statement of the form Sn converges in distribution to a Gaussian. Now, at the moment, we haven't imposed any kind of uniformity constraints. Indeed, the example that we saw on the last slide, where the sigma nk's were equal to the square root of n, shows that we can't expect to get Gaussian concentration in general. We need to introduce some average uniformity constraints. So here are a couple of examples of such constraints that we might use. We'll say that the array satisfies the decaying variance condition if along each row the maximum of the variance tends to 0 as the row number n goes to infinity. Now in the counterexample on the first slide, if we take sigma nk to be of the form sum bn divided by the square root of n, then this condition is just the condition that bn squared over n tends to 0. In other words, bn has to be little o of root n. So the counterexample we gave with bn equal to root n shows that this is sharp, if this is going to be our condition for the central limit theorem. Now here's another natural condition not specifically to do with variances. We could insist on uniform asymptotic negligibility, which just means that the terms along each row converge uniformly to 0 in probability as n goes to infinity. That is, for any tolerance epsilon, the maximum along the nth row of the probability that the term in that row is bigger than epsilon absolute value tends to 0 with n. This is a fairly natural notion of the terms being small and comparable in size. Small was what we would get with just this term going to 0, but the maximum could still fail to go to 0 in that case, meaning that some terms along each row stay large while most of them get small, in which case an average could still be small, even though some terms remain large. That doesn't happen when we impose this maximum constraint. And it turns out that the decaying variance condition implies the uniform asymptotic negligibility condition. That is a simple application of Chebyshev's inequality. Remember, our assumption for our triangular array is that the terms x and k are centered. And so Chebyshev's inequality says that this probability for each n and k is less than or equal to the variance of x and k over epsilon squared. Now just taking the maximum over k less than or equal to n, and noting that that variance is the definition of sigma nk squared, the decaying variance condition guarantees that that goes to 0, which shows that this maximum also goes to 0, and so the uniform asymptotic negligibility condition holds as well. It's pretty clear that UAN is strictly weaker than DV, however. Indeed, this condition here doesn't actually require second moments to be finite at all, and so this must be stronger, even in the case where second moments are finite. What we'd love to do, motivated by our sharp counterexample on the first slide, is show that independence and decaying variances are enough to give the central limit theorem for a triangular array. But that's not quite enough. We're going to need something even a little stronger than the decaying variance condition, although we'll later quantify exactly how much stronger it is. We need the Lindbergh condition. The Lindbergh condition says that if we cut off the calculation of the variance with the variable being larger than some epsilon, then the sum should go to 0. That is, this sum tends to 0 for any cutoff epsilon. Remember, this notation here with the colon means the expected value of this random variable times the indicator of the event that x and k is bigger than epsilon in absolute value. To understand a little better what this says, notice that because of our assumption that the sum sigma nk squared is equal to 1, the Lindbergh condition is actually equivalent to the condition that this sum tends to 0 as n goes to infinity. And that shows more clearly that this says that all of the terms are small and no term dominates the sum. For any epsilon, these cutoff variances are so close to the true variances across the board that the sum of them converges to 0. Now let's look again at our basic central limit theorem example. Suppose xnk is given by centered xk divided by square root of n times b. For IID random variables xk of variance b squared, well then the sum in the Lindbergh condition can be rewritten like this. And note that each term in this sum is an expectation of a function of the centered xk. By the identical distribution of those, all of those terms are equal. And so the sum divided by n here is just equal to a single one of those terms, for example, with k equal 1. Now, unless we're in the trivial case where b is 0, which we'll ignore since it's easier to analyze on its own anyway, for any positive epsilon, this cutoff grows as n grows. And since x1 is an L2 random variable, by the dominated convergence theorem, you can check that this expectation goes to 0. Hence, our classic example for the central limit theorem also satisfies the Lindbergh condition. It is weaker than the assumption of IID random variables. On the other hand, it is stronger than the decaying variance condition. Let's see why. The variance, sigma nk squared, because of the centering assumption in the triangular array, is the second moment of xnk. Now we'll simply break up that second moment with the indicator that the variable is less than or equal to epsilon plus the indicator that the variable is greater than epsilon. Now for that first term, xnk is less than or equal to epsilon, and therefore this expectation is certainly less than or equal to epsilon squared. For the second term, we'll go ahead and make the super blunt estimate to estimate it above by summing all of those terms, j going from 1 up to n, of the expected value of x and j squared, of which this actual quantity appears as only one term in this sum of non-negative terms. The reason why it's okay to make that blunt estimate is that the assumption of the Lindbergh condition is exactly the statement that this sum goes to 0 as n goes to infinity. And in particular, that means that this term goes to 0 uniformly in k between 1 and n. Therefore, by taking that sum, we also see that the maximum over all k less than or equal to n of sigma nk squared is less than or equal to this, which is bounded by epsilon squared plus something that goes to 0. It follows that the lim sup of the maximum over k of sigma n k squared is less than or equal to epsilon plus 0. And that's true for every epsilon positive, and so we can conclude, therefore, that the limit of the max variance across each row tends to 0 as the row number n goes to infinity, and that is exactly the decaying variance condition. So the Lindbergh condition is in fact stronger. Now we're in a position to state our main central limit theorem here, the Lindberg-Feller central limit theorem for triangular arrays. Under the same normalizations as we've been assuming, we have a triangular array. All of the variables are centered, independent along each row, L2, and arranged so that the variances along each row sum up to 1. Then if Sn is the sum of the terms in each row, if we assume the Lindbergh condition holds for the triangular array, then the sums Sn converge weakly to standard normal distributions. Conversely, if we know that the sums converge weakly to standard normal distributions, and if we know they satisfy the decaying variance condition, which we saw is actually weaker than the Lindbergh condition, then in fact we do get the Lindbergh condition. Thus what we see here is that while the Lindbergh condition is not stated in a way that makes it necessary and sufficient for the central limit theorem, the difference between the sufficient Lindbergh condition and the necessary decaying variance condition is precisely weak convergence to a Gaussian, and so these two are closely tied together. The next lecture will be devoted to the proof of this theorem, but before we head there, I'd like to conclude with one historical note about another generalized central limit theorem that predates the Lindbergh-Feller, and that is the Liapunov central limit theorem. Liapunov introduced yet another condition guaranteeing average uniformity, which we now call the Liapunov condition, and it's written right here. The assumption is that there is some alpha strictly greater than 2, so that not only are the terms x and k in L alpha, but so that the sum of the expected values of x and k to the alpha converge to 0 as the row number tends to infinity. That's the condition that Liapunov stated to conclude the asymptotic normality in the central limit theorem, but it turns out the same proof works with an even weaker condition. We merely need to assume that there exists some non-decreasing function phi on the positive reals, which is strictly positive on the strictly positive reals, so that xnk squared times phi of xnk has expectation that sums along each row to something that tends to 0. That condition implies a central limit theorem, and the reason is that it implies the Lindbergh condition. Indeed, assuming the Liapunov condition, consider the sum in the Lindbergh condition. Now for each epsilon, note that by the non-decreasing assumption on the function phi, t being bigger than epsilon implies that phi of t is bigger than or equal to phi of epsilon. Or in other words, since phi of epsilon is strictly positive, we can divide by it, and phi of t divided by phi of epsilon is greater than or equal to 1. But that means that on this set where we're assuming that xnk is bigger than epsilon, phi of xnk divided by phi of epsilon is bigger than or equal to 1, which means that this term is less than or equal to this, and of course that's less than or equal to the same term where we drop this indicator function and replace it by the constant function 1. We can then take this phi of epsilon out front and get this bounded by this. And so now, taking the sum over k along each row, the Liapunov condition is the statement that this tends to 0, and therefore this sum tends to 0 for every epsilon, which is the Lindbergh condition. Notice that Liapunov's original condition with a power bigger than 2 is just the special case of this, where the non-decreasing function phi is phi of t equals t to the alpha minus 2. Hence, the Liapunov central limit theorem is a special case of the Lindbergh-Feller central limit theorem, which is our next goal to prove.